So hello, my name's Paul. I work at Etsy, and we're going to go through today what Etsy learned building a distributed tracing system. Before we get stuck into that, just quickly an overview of what is Etsy. Etsy is the marketplace that we make together. It's a marketplace of handmade and vintage items, and it's a busy marketplace. Last year, we have over 1 million sellers, and last year they transacted over $1 billion between buyers and sellers distributed across the world. So this talk is what Etsy learned building a distributed tracing system. If that's not the talk that you're expecting, then by all means, make a run for the doors now. Before you go, though, here are the spoilers you can take back with you. You're building a product. This isn't rocket science. And having both the client and server observations is a really powerful thing. So this talk is, what did we learn? But before we can really cover what we learned, we should probably at least get some idea of what we actually built. And then if we want to know what we actually built, we probably need to know why we needed it in the first place. So let's start there. So why did we actually need a distributed tracing system? Let's start by thinking about what Etsy actually is. It's your old school LAMP stack, Linux, Apache, MySQL, and PHP. If you're paying attention, you'll notice that those are actually in the wrong order, but they look better like that than like this. Etsy has a somewhat infamous aversion to services and that three-letter acronym SOA. So we embrace our monolithic tendencies. We're not completely dogmatic, though. We have some exceptions where it makes sense. So we have search, which is based on Solr and Elasticsearch on JVM, a payment system, which is separate for compliance reasons, and a photo stack because it made sense in terms of the storage. So putting those things to one side and concentrating just on the monolithic LAMP stack that we have, this stack actually has some really nice properties for a scalable system. We're single-threaded, we're short-lived, and we're shared nothing. A request comes in, a PHP interpreter starts with a blank slate, builds up some context, loads in some configuration data, gets the framework up and running, services the request, sends a response out, and then throws away everything it did in that process. So this means that we can, we're only running for a few hundred milliseconds. And we can throw away all that state and start over afresh the next time. So this is something that we really value because we deploy continuously up to 50 or 60 times a day. We're pushing changes to the website, and they just get picked up by the next request that sees them. So this is really nice. This is some lovely properties if you're kind of scaling out a big website. But it does raise a bit of a problem with it, which is that we're single-threaded, and so therefore it's sequential execution. We're executing, and because we're in a single thread, there's nothing we're going to do if we go off to the database for a query. We're just going to sit there waiting for the database to come back. And that's fine because that process won't be actually busy doing anything on the CPU. We'll get woken up when the database comes back, but it still means that all that work that we want to do has to happen one thing at a time. And so therefore, as our application gets more complex, we're then increasing the lower bound of our response time because we're just saying that more things have to happen, and they have to happen one after the other. So that's true not only of our website, but also our API. And the API is important here because the API actually powers our native apps. So as you might expect, we have a series of applications, and we support iPad, iPhone, and Android tablets and phones. And this is actually out of date because we've now released, since these applications, we've actually released seller-specific applications as well, which help them run their shops and manage orders and things like that. So we're kind of we have a bit of a tension here where we have the nice properties of a single-threaded, short-lived, shared nothing architecture, but at the same time, we want to be able to do more things at once. So this is, we have this sequential problem, and we can't really, because we throw everything away at the end of the request, we can't kind of use that to get rid of some of the busy work that we may otherwise have to do. This also leads on to kind of a tangential organizational problem rather than a technical problem, which is that the native mobile apps are always playing catch up to the web. People, when they're building features, their mindset is desktop website. And so they build features on the desktop website, and they write the code, and we have a loose MVC kind of approach to things. And so as you might expect, all that logic doesn't end up in the model, it ends up in the controller, and the controller is not reusable in an API context. And so then it becomes a place where feature development is on the web first, and then maybe we'll get around to actually adding it into the API, and then the mobile teams can then adopt those features and expose those features and experiences to our members. The problem with this, as you may expect, is that this is increasingly disconnected from reality, this mindset. Mobile devices make up over half the traffic that we see on the site, be it mobile web requests or API requests for the mobile apps. And so the organizational problem we have is that we actually need an approach to unify the platform, so that there's one kind of Etsy and everything can make use of it. So we have these two problems, and the answer that we've settled on now is that we're just going to keep doing what we understand. We're not going to make any drastic, radical, earth-changing, any big changes to the system, but we're going to keep having PHP executing requests in a sequential fashion, but we're going to, as well as that, start making HTTP calls in an asynchronous manner. And so one request comes in, PHP starts working on it, and it can actually farm out some work using asynchronous HTTP and just say, these are all the things I want doing, and it will just sit there waiting until the slowest one of those comes back. And that's the approach. So we went and found a primitive, a concurrency primitive to build on top of, which is multi-curl. And this allows us to make these asynchronous calls, because pretty much nothing else in PHP does. And we built a lightweight API framework to support this approach. So I went and spent 2 days actually at Netflix and talked to their API team and had a real deep dive into how they approached the problem in a similar, they have a similar kind of problem where they have a much bigger proliferation of devices. They're supporting thousands of different devices, be it from Xboxes to iPhones or whatever. And so they came up with the decision to kind of not having the API team support all these devices, but instead have the device teams give them some ability to change the API to match the requirements. And so they offer like a scripting layer on top of their API that device teams can write endpoints that are specific to what they need. And I basically said that we should just adopt this wholesale for us. So we now have two kind of concepts with API endpoints, the first of which is a component endpoint, and the second of which is a bespoke endpoint. A component endpoint is simply your traditional kind of RESTful endpoint that returns a resource that's generic, and it's a domain object of some type in our system. So it's a listing, it's a shop, it's a member, or whatever, or a favorite. A bespoke endpoint is written with one client in mind. And the idea is that it can go and find a whole bunch of these domain objects and compose them into a single response to return to the client. Both of these can also make use of the HTTP concurrency to then kind of go off and make additional calls to go do their data fetch in a faster manner. So there is this bespoke component divide, but actually the interesting part really is the concurrency. And to kind of solve the organizational problem, we're now trying to advocate for an API first rather than a desktop first or a mobile first approach. Is actually just write some API endpoints and then start building things on top of that. In that model, the website itself is a consumer of this API. So this is the new programming model we have. And one of the features that we've launched on this is the activity feed. So if you're a signed-in member of Etsy and you go to your homepage of the site, you'll see this kind of view, which is showing things that we believe, activity that we believe is interesting to you. So if you follow people on the site, you'll see activity they've been up to. If you follow shops, you'll see activity they've been up to, and so on and so forth. So to build this page, there's a series of bits of data that we need that we're interested in having. First of which is the activity feed itself. And this is made up of a series of stories, and they might be listings, they might be shops, they may be people that you should be following, that we believe you should be following, or other kinds of activity. Now that goes a lot further down than this slide shows, but there's probably 24 items displayed here. Secondly, we have the sidebar here, and this has got information about recent blog posts and featured shops, which is a kind of a daily, like, rotational thing where we show new shops and we feature, sellers that we think are amazing and we want to share with the rest of the world. On top of that, we have our picks for you, which is recommendations. So we have a data science team that are writing all these really complex and interesting recommendation models, and this is one of the outputs of that system. And then on top of that, it's items from shops that you follow that have been favorited recently as well. So it's kind of bits of content. The real thing, though, is that there's 4 main bits of content here that we're interested in getting. But also, this page can actually be refreshed using Ajax. So we need to be able to support that as well. So all this data needs to be available as a single Ajax endpoint as well. So if we just quickly go through a flow of what kind of requests we'd see in this world, we'd have the homepage request as you come in and you say, can I have the homepage, please? We'll make a call to the Bespoke Ajax endpoint, which has got all the data that it needs. That Bespoke endpoint, when it receives that request, is then going to make 4 requests itself. And of those, the sidebar at the bottom there will go off and make a couple more calls to find some blog post data and another one about featured shops. The activity feed, which has all those stories in, will actually go off and make many more calls. And so each one of those story cards is a separate call in its own right. So you look at this model of what we built, and then you turn around and think, we may have just accidentally built an RPC system. So we started from a place where we had single-threaded, short-lived, shared nothing as an architecture. And those were lovely properties that we have for horizontal scaling and continuous deployment. And in this model, where are we now? And we're now in this kind of middle ground of, actually, there's many of these short-lived, short-threaded, single-threaded processes. There's many short-lived processes happening on. And is it really still shared nothing? Because we're kind of making calls across the cluster at this point. And we're dependent upon all those calls to be able to return a response. And so this then, highlighted something that was that our existing introspection tools were built for a much simpler time. Our whole model before now had been, we start a request at time 0, and at time t, we finished that response, and we did a whole bunch of things one after another. In this new world, we're doing a whole bunch of stuff at once, and they can be on many hosts across the cluster. And we're not entirely sure what's happening, because you're writing code, and you have no way of really seeing this. So we needed a way to visualize this execution tree. And this kind of is the rationale. This is real, the impetus for us to build this. And so then we went about thinking about, right, what actually do we need to build for this? And so at this point, you can kind of just stop and take a look around and think, well, what have other people done? And clearly that's been a topic, I think, of this conference, is people talking about looking at papers. And sure enough, the answer here is just simply to read Google's paper on Dapper. It was published in 2010 and describes the system that they built to allow them to trace through their distributed RPC system. So we have that. The slightly longer answer is actually to read Dapper and then look at Zipkin, and we started then playing around ourselves to see what it would take to build one. So Zipkin is an implementation of Dapper that Twitter released a couple of years back, and it's what they use in production to trace through their distributed RPC system. So that's great. It's open source, and you can go look at the code. So using that, we kind of went and looked at the code, and then started putting together a prototype for ourselves. And sure enough, you kind of run into some problems. And so while prototyping, I kind of ran into some issues, and I was just doing the thing that everyone does now, which is rant on Twitter about stuff. And if you see at the bottom there, there's actually a reply from James, who's sat at the back here, who works for a company that offers tracing as a service. So through just ranting on Twitter randomly, I was discovered by someone else who put me in touch with that company. So we have Twitter. We have Zipkin from Twitter to consider. And now I know about this other thing, which is a commercial product, which is called TraceView. And so then we're kind of in a world then, and then through having talked with James, I then got in touch, was actually discussing with one of their engineers, Dan, who kind of built the system. So I managed to talk to him and see what problems he'd run into. So then you're with the traditional kind of decision then of, do you build this or do you buy it? And clearly these days, there's a third kind of stance, which is, or do you adopt something? Because open source solutions are often available, but they're not free. To kind of seriously take on an open source product, you really need to sign up to fix bugs potentially in it, and then also ingest any dependencies that that open source project requires as well. So in the Zipkin case, it's a product written in Scala that obviously runs on the JVM. It uses Thrift and Scribe as a transport layer to move data around in the system. And Twitter used Cassandra as the backing store for this. And of those, we have a little bit of Scala, but not really in production in terms of the website. And we have Thrift, but we don't have Scribe. So at the very least, for us to be able to instrument our application, we're going to have to get Scribe up and running and know what that means. And so kind of we looked at that for a bit, and we'd been doing some prototyping, and we're feeling quite good about the prototyping, so we just decided we'd carry on with that and build it out to be the full thing. So then that's it. We're then trying to build out this thing to be a fully distributed tracing system. So we should probably just quickly cover what it means to have a distributed tracing system. So all the implementations that I've mentioned so far operate on the concept of a trace. And a trace is simply a tree of execution. And so in that tree, each node in that tree is a span of execution, a single span of execution. And the span is made up of a series of observations about a single service call. So those observations in the literature are kind of termed annotations, and they include a timestamp of when this annotation occurred, and optionally a duration. And the duration is actually like how long it took to get to the point when it was done. So the timestamp is the endpoint, and then the duration is effectively the beginning point. So that approach makes it easy to kind of tie annotations in with instrumentation you may already have in your application. Because if you already have a duration, then you just need the timestamp, and you can kind of add it straight in. So if we go back to this model of the execution that we're doing on behalf of just rendering a single page request, and if you squint and just turn your head slightly, you can then actually see that this is a trace tree. And that you can see clearly the parent-child relationships between them. And in this instance, the root of this tree is the originating request, which was to render the home page. If we take this tree and kind of resize how each of these nodes are shaped in this tree, such that the width that they actually took to run, and we position them on a timeline of 0 milliseconds on the left to 330 milliseconds on the right, then you can kind of see we end up with this interesting diagram kind of showing exactly what was happening at what point during this request. In this diagram, vertical dotted lines simply denote parent-child relationships between these requests. And so then now our goal is to write a system that will collect enough data that will allow us to actually recreate this diagram from an actual tree of requests. So that's distributed tracing in a nutshell. So that's what we need to have. That's what we're working towards having at the very end of this, but how does that actually break down in practice in terms of building this system? There's 4 main pieces to the system. We have instrumentation, where we need to collect observations up in the application. In the data collection phase, we want to be able to kind of store all those observations centrally, and then we want to be able to retrieve them later on to recreate this single trace, and then obviously visualize that trace from the data that we've retrieved. So those are the 4 steps, but before we can even get there, we need to actually be able to tie together these requests so that we can we need to tie together these disparate threads of execution, and so that we know where they live actually in this tree. So in our model, from having read the Dapper paper, what we're doing is we're just simply passing down tree location data between requests. So for any HTTP call, we're going to pass down some headers that say where this new request that we're just making, it lives in a tree. This is the only code slide in the entire talk, so don't worry about it. I'm not going to put too much PHP in front of you. The important thing to note here is that the code manages these headers for you. So we can ask it to say, we're about to make a new request, what headers should I pass down? And we get 4 headers back. The main ones that we're interested in are the request identifier that we're going to tell the server when we send this request, this is your identifier for the request you're about to do on our behalf. And then we pass down a parent identifier, which is us, and then the originating request identifier, which is effectively the root. So in this model, the client is instructing the server to say, this is what your identifier will be for the execution you're just about to do for us. And so we just simply pass those off to curl when we make a call, and then the receiving server, the code knows to kind of look for those headers, and if they're there, kind of set up the whole environment so that they can then be passed down subsequently further down the chain. Anything that's not HTTP in this world at the moment is instrumented purely from the client's point of view. So when, with a HTTP call, we have the client, which is curl, and we're running curl to make this request. And on the server, we're going to receive a request and do it. So from that point of view, we actually can get both sides of the point of view of that request-response cycle. We can see what the client thought was happening, and then we can see what the server thought was happening as well. For anything that's not HTTP, like making a database query or talking to Memcache or Redis, we only really have the client's viewpoint. So they become, at least for now, leaf nodes in this tree, and we only see what the client experienced in sending a request and then getting a response back from that service. So with those requests linked together, when we position in a tree, we now want to obviously collect some instrumentation data about this. So in that HTTP communication, there's at the very least 4 events that happen during that span, so that we can, these are observations that we can make. The client sends a request, the server receives the request, the server works on it and sends a response back, and then clearly the client then receives that response. Even in a distributed system where there may be clock skew between these nodes, we know at least that these events must have happened in this order, regardless of clock skew. Even if timestamps don't agree, they have to have happened in this order. So this is the very minimum that we're going to have. But because we can add arbitrary annotations in to say, oh, I just did this and it took this long, we can add annotations in at the higher level. So in our code, we can kind of say, OK, I'm just about to go do a database query. And you can add that annotation in at maybe like the object relational mapper level. So at that point, you can see, OK, I'm about to go make a database query, but the ORM in that instance may actually go off to Memcache first, not find the thing it's looking for, and then fall back to a query, and then actually set that back into Memcache. And you can see that that actually appears in a single kind of, it's the parent annotation then in that model has all those 3 things. And you can see, OK, that's the ORM doing its thing. So that's at the high level. And then anything where the server is actually going to go make a service call, so go over the network to something, is handled by a child span. So in that world, we create a new span with us as its parent, and then that's then the series. All the observations then are collected under that one span. And then, as I was saying, there's at least 4 things that we'll have. The last 2 of those, which is the server sending a response or the client receiving a response, is a terminating kind of annotation, because clearly nothing else can happen from that annotation's point of view, from that span's point of view when that happens. So at that point, then, that just logs the data that we've collected up, the series of observations. So that's instrumentation, and then we've got the other 3 pieces, which is the collection, the retrieval, and then the visualization. So for that, this is kind of the data flow that we have going on across our system. In terms of the instrumentation, that all happens on a web node is executing some code, and during that single-threaded execution, it's collecting up these things. And then when it hits one of these triggering annotations, we log out. And so to start with, we use JSON to just log out the annotation, all those observations as a serialized kind of form. But we found that to be too slow, so now we do this admittedly hacky approach, which is where we message pack it, we gzip it, and then we base64 encode it, because then that gives us something that's kind of ASCII safe. It's a log line. We know it's going to be new line delimited, and then we can use our existing kind of infrastructure to kind of handle that, because this is just a log file at this point, and we know how to handle log files. So those log files get forwarded into Logstash, And if you've not come across Logstash before, it's like a Swiss Army knife for collecting log files and from multiple sources and then emitting them to some other source. So for us, Logstash actually takes these serialized spans, deserializes them back from our hacky format, and then posts them into Elasticsearch and indexes them there. And so then Elasticsearch is our retrieval system. We used Logstash and Elasticsearch because at the time I asked around the company what people were suggesting, and I found that the operations team was in the middle of a rather large migration from an unnamed proprietary log processing system to something that is not so proprietary. And so we were actually the first customer of that system internally. And so it was great because we got to work very closely with the operations team while they were standing this thing up in production. And they were happy because we had some data flowing through it that wasn't critical, and we could kind of mess around with it and try and work out what we needed to make the system do. So yeah, you can kind of take Logstash and Elasticsearch, and then there's also a front end for it, which is in a screenshot, which is called Cabana. And that's then, if you have just log files, that's the kind of search interface for that. So that's data collection. The retrieval is just simply an API endpoint. We can request from that endpoint, show me all the traces that the system has. And then if we want to look at one of those traces individually, we can then request it. And the API will go talk to Elasticsearch and just query it for all spans that Elasticsearch have that share the same trace ID or the same root. And then we take that data, we munge it around a little bit and order it back into a hierarchical time-ordered series, and then send that to the browser for it to be rendered then into this trace diagram, which is the same as the diagram we were looking at earlier, the drawn diagram. We use D3 for that, which is a lovely JavaScript library, but it has a very particular take on the world to the extent that the best thing to do is go find an example that does something like you want it to do, and then just hack it to make it work. And that's the only way that I got this working, and then I managed to find someone who knew better than me, and they actually made this into a zoomable icicle model, which was great, because my first attempt was awful. So that brings us on to the visualization. So we have all this data, we can have it in the browser, and then we actually want to be able to display it. So this is the user interface we have now to cross-stitch. It shows a kind of, it's called a waterfall model, but I'm not sure if it really is a waterfall chart. I'd love to hear if you have a good name for this. So just running quickly through the user interface, we have a legend up here. And the interesting thing to note is that this was actually a request for the home page. And so in doing so, we made 43 HTTP calls and used up 2 seconds worth of HTTP time, which is clearly quite a lot of time for a single request. But on the upside, we did get it done in just over 350 milliseconds. So the user didn't experience that, but obviously our cluster did. This is the root request. So this is the actual request that came in from a browser. We spent some time running from 0 to 360 milliseconds, and then we returned the response. Something that the system kind of can highlight for us is that we have some bootstrapping costs. This is because, obviously, it's shared nothing, so we need to get some stuff up and running. We need to get configuration values up and running. We need to get the framework up and running. And then we get into actually doing the interesting work of specific to this request. So during that request, it's doing a whole bunch of data collection, data fetch. And you can see that actually these are the 4 HTTP calls that the system made. And so they're the darker purple bars on this. Anything that's a dark purple bar is a HTTP call. Lighter purple is annotations on that call. And then the other colors are the other data sources we could have. And then the activity feed stories endpoint, which goes off and gets us all their stories, itself then goes and makes a whole bunch of HTTP calls as well. So this is obviously a lot of fan out, and that actually goes down to the to get to the total of the 43 calls in total. And then once all that data comes back, the root request then actually kind of then does the rendering part. So it takes all that data and runs the template through it. It's still in a period of migration, so we still have data fetch happening in templates, which always boggles the mind, but this is just the nature of the beast, is that when your templating language happens to be your code language, then all bets are off in terms of being able to enforce stuff. So we still have a little bit of this because not everything is migrated to API first, but when we kind of get to that world, there'll be a network boundary between rendering and data fetch, and so therefore you can't just in the template arbitrarily go and run some SQL or go query memcache. So that's what we built. What did we take away from this? What are the interesting parts of this? I think the number one thing is that this isn't rocket science. I was initially kind of wary of this topic because it was distributed tracing, and I was kind of like, well, we don't do that. I mean, we have distributed systems. We've got obviously lots of machines, but we're not doing anything that needs to worry about consensus algorithms or all the rest of it. And so it kind of scared me off a little bit. But I stuck with it, and the Dapper paper is actually really readable. And having an open source implementation already available to look at is great. So this isn't rocket science. Most of the code is actually specific to your environment. Most of the time, I was just going off and instrumenting stuff to get more data into the diagram. And that's where all the work really went. And so therefore, there's nothing I'm announcing in an Etsy fashion to say, and here's something open sourced. So sorry about that, but the point is you could do this yourself without much effort. It's simple to write and can be done piecemeal. My first prototype of this was just simply showed that we could link together HTTP requests and then show a visualization of the HTTP requests that had been involved in a single trace tree. And then over time added in more things and kind of recruited other people to instrument bits and pieces here and there. On a philosophical note, internal tools are really no different from new products. If you're a product company, or even if you're not a product company, if you're building a tool for internal use, then it is a product. There's an adoption curve, and it's your job to accelerate it. So I spent quite a bit of time kind of telling people how great this cross-stitch thing was, and trying to do lunch and learns internally to try and drive adoption. Found feature teams that were starting to use the API-first approach, and kept putting it in front of them to show that they could actually find issues with what they were building, or kind of diagnose things ahead of it being really a problem. So the first version was end-to-end complete. And another takeaway is to get cross-discipline input. Because I went around and asked people about this issue, I kind of got some advice from the product designers. Clearly, they didn't have any time to actually do a user interface for me, because that's why we've got what we've got, but they kind of helped with colors. And that was super useful to kind of get something that looked better than me picking arbitrary RGB values. And from talking with the operations team about what options do we have for me being able to kind of log this data on each of these nodes and then somehow centralize it and then somehow retrieve it, that raised the issue, the fact that we were kind of already putting together a Logstash Elasticsearch cluster. It is product development. Regardless of what you think about this, if you don't believe it's product development, you're wrong. And if you're building tools for others to use, then you're building a product and you should treat it as such. Another thing that we learned, actually, the client-server point of views and being able to correlate those two is extremely powerful. It makes network latency easier to observe. Now, obviously, there's still clock skew, so you can't use it for exact timings necessarily. But it did help highlight one of the first teams to pick this up, which was the homepage. They had, as we saw, the request that came in to render the homepage made a call to the Bespoke endpoint. And we hadn't incorporated that into our framework that we built for building API endpoints. And so they'd gone and written their own curl wrapper. And then they were saying, it just seems to be really slow. We seem to kind of just spend hundreds of milliseconds waiting for this Bespoke endpoint. And so we managed to actually load up cross-stitch and have a look at it. And so see, sure enough, there was almost 100 milliseconds before the server had even received the request, and then another 100 milliseconds before the client received the response from the server, because we had those two correlations. And so I went and talked to the network's operations team, and I was like, that's not to be expected, surely. Like, this is all within our own data center. We're no more than 3 or 4 hops away from anything. And they confirmed that definitely that shouldn't be happening. So we took another pass at their curl library and found that the host name they were using was actually www.etsy.com, which is all well and good, but if you actually resolve that, that goes to one of our CDNs. And so they were going from our origin out to a CDN, back into origin, and then the response was then going back from origin to the CDN, back to origin again. And sure enough, that will give you some network latency. So we changed that to be the right internal address that went directly to the load balancer for the API cluster, and that latency magically vanished. Another thing that we noticed from doing this is actually areas with few observations are actually the interesting parts of your application. Because if you don't have any service calls in a certain time span, then that suggests that potentially you're actually just looking at something that's running on the CPU. So if we look back at this trace, there's this section just before 300 milliseconds where for 30 milliseconds we have no observations. There are no service calls that are happening during this time frame. And so I haven't looked into this because I only really noticed it when I was putting the slides together, but I want to know what's going on there because potentially we're doing something silly. Or it's something that we need to do, but we're maybe not doing it efficiently. Or we just don't need to do it at all. And so that's something to go and look in. And so then my approach now would be to go find the annotations either side of that, and that gives me an upper and lower bound of like kind of tracing through code. I know, okay, so we did this, and then something happened, and then we did this. And so it's that something happened, then you can kind of have a look at there. Another thing that this architecture, rather than the distributed tracing, points out is that clearly shared nothing isn't actually free because you have this bootstrap cost. That's all well and good if your request is hundreds of milliseconds to do the whole work. But if you're doing lots of little ones, then you're actually paying this bootstrap tax all the time. And the irony is that the faster you make your API responses, the bigger the proportion of the time you're paying the bootstrap cost. And so therefore, you're spending more of your cluster time just doing not busy work, but doing just bootstrapping to get to the point to do something interesting. Specifically, the questions that I'd like to be able to answer is, was that 40 millisecond memcache call, were we just unlucky? Is that actually something we see a lot of? Is it something we see on a specific memcache host? Or is it something we see on a specific client? And because we have this data and it's on the level of individual spans of service calls, we can make those, we can answer those questions because we can query based upon those things. Another thing that we're looking at doing is a hybrid API client because clearly if you're making a lot of calls out that are very slow and a lot of calls that are very fast, you're potentially spending a lot of time waiting for those calls to come back. And in that time frame, that process is doing nothing. And so we could maybe save the bootstrap cost by just interleaving small units of work that we know are short API calls and interleave those because we've already paid the bootstrap tax in that process. So that's something that we're actively looking at what we could do then. And something else that some of the other teams are actually looking into seriously is instrumenting other things that aren't just HTTP. So the search team have seen this and they love the look of this, so they want to instrument now, looking at instrumenting, I think, either Solar or Elasticsearch, with then being able to see what were the threads in that JVM doing, which ones were kind of busy with work for this specific request. And so we can then not only just see the network boundary of we spent this much time waiting for a Solar response, but then see what Solar was doing internally as well. Something I'd love to do is kind of ramp up the sampling rate so that we actually get all data. Obviously, that's going to require some rethinking of the logging format, and maybe we'll have to actually adding some much more clever sampling so that we actually send all these traces over to a collection system, and that collection system and then can discard uninteresting traces. So if it was a 200 response, then we sample that at a much higher rate. But if it's an error response, we maybe keep all of those so that we can then correlate errors that we've seen in our logs with a trace that showed us what was going on in that entire tree. So that's pretty much it. That's why we needed it, what we built, and what we learned. Thanks a lot for your time. I'm Wright on Twitter if you want to ask any more questions, or obviously you can ask now. Or not. Yes? Yeah, so the question was, does writing all these logs in production introduce performance issues? And it hasn't been enough of a problem for us to worry about now. If and when it becomes more of a problem, such as we start, if we start sampling at a higher rate and then we start to see I/O issues, then potentially we would then outsource that to kind of a local service that will collect that up and then flush them bulk to disk. But our web servers run on SSDs, and actually all the application code lives on RAM FS, so the SSDs are really kind of quite quiet, and they have nothing really going on. Anything else?
Most of your clients use this as something when the site feels slow and they want to figure it out, or they kind of made away from this almost feel like this simulation you just kind of check periodically and find hotspots?
I think,
that's the hardest part of getting people to adopt.
yeah. So the question is, do people use this all the time, or do they use it only when there's problems? And for some teams that are looking to constantly kind of improve their products, their features, they look at this all the time. Other teams, only when they're experiencing performance issues. But it's all part of the kind of adoption thing, and it's also about the focus of the team as well, because a team like data science will spend a lot more time about the quality of like recommendations rather than the performance of recommendations, and that's perfectly valid. Yep.
What do you search by? Is it by the root API endpoint, or how do you find an interesting trace?
So the question is, how do you find an interesting trace? What do you search by? Because it's in Elasticsearch, you can just ask Elasticsearch for all root span IDs by asking for all spans that don't have a parent. And by definition, they're the roots of these trees. And with that, we can then see URLs and other bits and pieces. And then when you want to get a trace, you just you click on one of those, and then you find all spans that share the same root, the same root ID, and then that's your trace. Yep.
How are you guys tracking the timestamp from start to end on all the different servers? And you have like all your times synchronized across all your servers. So there's some kind of variance there, right, where you could be off by half a second?
Yeah, there's clearly, so the question is effectively, what about clock skew? And we kind of throw our hands up, really. The rendering just finds the minimum of the start annotations, which is client receive and server receive, and the minimum of the client receive, and I'll start again. We take the annotation, which has 4 things in it, which is client send, server receive, server respond, client receive, and we just take the minimum of those, the first 2 and the maximum of the last 2, and that's then the upper and lower bounds. And clock skew will be clock skew. Anything else? Okay, thanks a lot.